Excellent. Ta-da.
All right, we're ready to go.
Okay. Nick, would you like to share your screen and begin your presentation?
Yes.
Oh, that's gorgeous. That's beautiful.
Today, I'm going to share knowledge of how GIA use advanced analytical techniques to analyze the chemistry of gemstones in order to understand the cause of color in gemstones, detect the treatments, distinguish natural from synthetics and imitations, classify gemstone species, and find out which country gemstones may come from. In the 90-year history of GIA, great changes have taken place in identification and analytical instruments. These changes have been closely related to the problems to be solved in the gem identification laboratory. As time goes, the jewelry industry has higher demand for the gem identification, which requires the laboratories to constantly improve themselves to use more advanced analytical instruments and methods to solve problems. This is a photo of GIA's headquarters on San Vincent Boulevard in Los Angeles, California in 1956. At that time, many basic gemological problems were the focus of gem identification, such as, what gem is this? Is it a red spinel, ruby, red garnet, or red tourmaline? This is a gemologist at GIA who is using a portable desktop refractometer to detect the gemstones. By measuring the refractive index of the gemstone, we can identify it accurately. As time goes, more treatments and synthetic methods appear in the jewelry trade. More in-depth problems have also been aided in gem identification, such as what elements cause color in gemstones, how to detect the treatments in gemstones, and how to distinguish natural gemstones from synthetics and imitations. In order to solve these more complex problems, GIA Laboratory also gradually began to equip large-scale analytical instruments. This is a photo of GIA's headquarters in Santa Monica, California in 1976. The scale of the laboratory was gradually expanded. GIA Distinguished Research Fellow Dr. James Shigley is operating an X-ray fluorescence spectrometer. For example, in ruby, filled with highlight glass, the presence of lead in the filler can be accurately measured by this instrument. Nowadays, the jewelry industry puts forward higher requirements for gem identification laboratories. People begin to care about the origin of gemstones. For example, is this ruby from Myanmar, Vietnam, or Mozambique? This Paraíba tourmaline from Brazil, Mozambique, or Nigeria? Most effective way to solve this problem is to use laser ablation inductively coupled plasma mass spectrometer to measure the trace element content in gemstones. The concentration of various trace elements in gemstones from different localities are different. This photo is the headquarters of GIA in Carlsbad. The gem identification laboratory where I work is located on this campus. This is a laser ablation inductively coupled plasma mass spectrometer in Carlsbad Laboratory. Carlsbad campus of GIA is a very beautiful place. If you are interested in gemology, you can sign up for gemstone identification courses in the school to learn more fundamental and practical gemological knowledge. Analyzing a gemstone's chemistry accurately has been very important for modern gemology. The chemical information of a gemstone can help us understand what elements cause color in gemstones, help us detect the treatments in gemstones, distinguish natural from synthetics and imitations, classify different species for a mineral group, and know where a gemstone is from. First, let's talk about what elements cause color in gemstones. To solve this problem, we need to use a key instrument called Ultraviolet-Visible spectrophotometer. It is mainly composed of a light source, a monochromator, a sample chamber, a detector, and a data processing system. The continuous spectrum emitted by the light source is decomposed into monochromatic light with specific wavelengths by the prism in the monochromator. The monochromatic light is divided into two beams of equal intensity. One travels through a blank background and the other travels through a gemstone. The detector automatically compares the ratio of the intensity of the two beams, that is the transmittance. After logarithmic transformation, the data processing system converts the transmittance into absorbance and records it as a function of specific monochromatic light wavelength. As the monochromator completes the continuous scanning of the whole continuous spectrum from long wavelength to short wavelength, the complete near-infrared, visible, ultraviolet absorption spectrum of the gemstone is recorded. First, I'm going to talk about different color-causing elements, in another word, chromophores, in different gemstones. The first gemstone I'm going to talk about is corundum. Corundum is a crystalline form of aluminum oxide, composed of aluminum atoms and oxygen atoms in a ratio of 2:3. It crystallizes with trigonal symmetry. Each aluminum atom is bonded with 6 oxygen atoms to form an octahedron. Many of these aluminum oxygen octahedra share some of their corners, edges, and faces with each other to form the framework of the whole corundum crystal. Pure corundum is colorless, such as this synthetic colorless sapphire. Corundum shows different color when other trace impurity elements, such as magnesium, titanium, vanadium, chromium, manganese, iron, cobalt, and nickel, replacing aluminum ions in the crystal lattice. Corundum has one of the widest range of color among all types of color stones, including red, orange, yellow, green, blue, violet, and purple in the visible spectrum. Chromium is a trace element primarily responsible for coloring ruby red and sapphire pink. When a small amount of aluminum atoms in corundum lattice are replaced by chromium atoms, chromium ion absorb purple, blue, green, and yellow wavelengths of light strongly, resulting in a relatively large amount of red wavelengths of light passing through corundum. What we see is ruby. When there are not so many chromium ions replacing aluminum in corundum lattice, a lighter colored pink sapphire is seen. Iron-titanium pairs are the primary chromophore of blue sapphire. Iron and titanium replacing aluminum in the lattice electrostatically attract each other and locate on adjacent aluminum sites in the crystal, forming the pair. The intervalence charge transfer between the two cations causes strong absorption of green, yellow, orange, and red wavelengths of light, resulting in a relatively large amount of blue and purple violet wavelengths of light to pass through corundum. What we see is blue sapphire. Now we know chromium causes red in corundum, while iron-titanium pair causes blue in corundum. The purple to violet color in corundum is caused by a combination of these two chromophores. Whether the hue is more purplish, violetish, or more reddish depends on the concentration of these two chromophores. Iron 3+ and Iron 3+ pairs replacing aluminum in corundum crystal lattice cause yellow color in corundum. The strong and wide absorption peak centered at around 450 nanometers absorbs blue wavelengths of light and results a general yellow color appearance of the stone. Iron 3+ and Iron 3+ pairs are very weak chromophores. It means that there has to be a very high concentration of this type of chromophore in corundum to cause a saturated yellow color. Most of saturated yellow sapphires with iron concentration higher than 5,000 ppmW are colored due to this type of chromophore. Now we know Iron 3+ causes yellow in corundum, while Iron-titanium pair causes blue in corundum. The yellowish-green, green to blue-green color in corundum is caused by a combination of these two chromophores. Whether the green hue is more yellowish or more bluish depends on the concentration of these two chromophores. Vanadium 3 plus replacing aluminum in corundum crystal lattice causes color change phenomena. The strong vanadium absorption band centered at around 580 nanometers creates two transmission windows. The transmission window A, centered at around 480 nanometers in the blue-green region, and the transmission window B, covering the whole red region from 620 to 670 nanometers. The daylight has more light emission in the blue-green region than yellow to red region. The transmission window A, the window in the blue-green region, gets emphasized, an attribute to the color of the stone dominantly. As a result, a blue to violet color is seen in corundum. The incandescent light has more light emission in the yellow to red region. The transmission window B, the window in the orange to red region, gets emphasized, an attribute to the color of the stone dominantly. As a result, a purple to red color is seen in corundum. Let's look at the color change again. Next, I'm going to talk about chromophores involving trapped holes in corundum. When the concentration of magnesium and nickel exceeds the sum of the concentration of silicon, titanium, and hydrogen in corundum, the trapped hole structure can form in highly oxidizing environments. The charge on excessive magnesium is 2+, while the aluminum being replaced has a 3+ charge. To make the crystal to remain electrically neutral, a missing electron, a hole, is created in the valence band near the magnesium to accommodate this discrepancy. We can look at this structure as magnesium 2+ oxygen 1- group called trapped holes. Trapped hole-related chromophores are very strong chromophores. It only takes a few ppma of trapped hole iron 3+ pair to cause an intense yellow to orange color in corundum. When trapped hole pair with chromium 3+ pair with chromium 3+, it causes orange color in corundum. It only takes a few ppma of trapped hole chromium 3+ pair to cause an intense orange color in corundum. There is an orange-pink sapphire called Paparasha sapphire. The word Paparasha comes from Sanskrit and represents a color of lotus. It is a very rare and precious sapphire. The pinkish-orange, orange-pink color is caused by the combination of iron trapped hole pair, chromium trapped hole pair, and chromium 3+. The next mineral I'm going to talk about is beryl. Beryl is a mineral composed of beryllium aluminum cyclosilicate. Gemstones such as emerald and aquamarine are famous beryl varieties. The dominant features in the structure are the hexagonal rings formed of 6 silicon oxygen tetrahedra that are stacked above one another forming planes. Aluminum and beryllium atoms lie between these planes. Each aluminum coordinates with 6 oxygen atoms to form an octahedron. Each beryllium atom surrounded by 4 oxygen atoms to form a distorted tetrahedron. In these positions, they link the hexagonal silicon-oxygen rings, and the whole structure is linked laterally and vertically to form the beryl crystal. Pure beryl is colorless, such as this colorless beryl called goshenite in the trade. Beryl shows different color when other trace impurity elements, such as vanadium, chromium, manganese, iron, replacing aluminum ions, or appear in the channels in the crystal lattice. Iron 3+ produces golden yellow color in beryl called heliodor in the trade. In iron-containing beryls, such as aquamarine, a blue variety of beryl, iron 2+ produces pale blue color. When iron 2+ and iron 3+ are both present, the color can be a dark blue. Green color is from a mixture of blue and yellow. Chromium 3+ and vanadium 3+ attributes to the saturated green color seen in emerald, a green variety of beryl. The pale pink color in morganite is caused by manganese 2+. Manganese 3+ causes the deep red color in some of very rare red beryl discovered from Wawa Mountain of Utah by Maynard Baxby in 1904. Some blue beryls originally found at Machixe mine in Brazil have color from radiation-induced color centers. The color is not stable and fade under sunlight. The color of the stone can be reproduced by irradiating it with high-energy particles such as gamma rays and neutrons. Chromium or vanadium or both of them are primarily responsible for coloring emerald green. When a small amount of aluminum atoms in Beryl lattice are replaced by chromium or vanadium atoms, the chromium or vanadium ions absorb most of green, orange, and yellow wavelengths of light strongly, creating a transmission window in the green region of the visible spectrum. What we see is emerald. The next mineral I'm going to talk about is spinel. Spinel is a group of mineral. I'm only going to talk about chromophores in one spinel species, composed of magnesium aluminum oxide, which is also the most common gem quality spinel. Spinel crystallizes in cubic crystal system. Each aluminum atom is preferred to bond with 6 oxygen atoms to form an octahedron. Each magnesium atom is preferred to bond with 4 oxygen atoms to form a tetrahedron. Many of these octahedra and tetrahedra share some of their corners and edges with each other to form the whole spinel crystal. Pure magnesium aluminum spinel is colorless. Spinel shows different color when other trace impurity elements such as chromium, iron, and cobalt replacing magnesium or aluminum ions in the crystal lattice. Chromium 3 plus produces red color in spinel. Cobalt 2 plus produces a bright saturated blue color in spinel. Iron in tetrahedral site produces a purple to pink color in spinel. Iron in octahedral site produces a grayish-green color in spinel. The color of most blue spinel is caused by a combination of cobalt 2 plus and octahedral iron. The color change spinel is caused by a combination of cobalt 2 plus and tetrahedral iron. Color of some very rare gray spinel is caused by a combination of tetrahedral iron and octahedral iron. I would like to talk about color change spinel in detail. We already know cobalt 2 plus causes bright blue color in spinel, while iron in tetrahedral site causes pink color in spinel. The combination of cobalt 2 plus and tetrahedral iron creates 2 transmission windows with equivalent strength in the visible light region. As a result, the color change phenomenon can be observed. The next mineral I'm going to talk about is garnet. Garnets are also silicates. I'm going to talk about pyroxide garnets first. Pyroxide garnets have 3 end-member species. They are pyrope, serpentine, and almandine. Pyroxide garnet has its Y site, the octahedral site occupied by aluminum. Silicon oxygen tetrahedra and the aluminum oxygen octahedra share corners to form a 3-dimensional framework. Within these, there are cavities that can be described as triangular dodecahedra of 8 oxygens, which contains X-site ions. In this case, the X-sites are usually mainly occupied by magnesium, iron, or manganese. When X-site is occupied by magnesium dominantly, it is called pyrope. Pure pyrope is colorless. Natural pyrope has a light pink color caused by iron 2 plus. When X-site is occupied by manganese dominantly, it is called serpentine. Pure serpentine is orange, colored by manganese 2 plus. When X-site is occupied by iron dominantly, it is called almandine. Pure almandine's color can be dark red or orange red. The color is caused by a combination of iron 2 plus and iron 2 plus, iron 3 plus intervalence charge transfer. We know iron 2 plus causes purple, pink, or reddish color, and manganese 2 plus causes orange color in pyroxide garnet. There are other major chromophores also causing strong color in pyroxide garnet. When a small amount of chromium 3 substituting aluminum in the perovskite garnet crystal lattice, causes a strong, deep red color. When a small amount of vanadium 3 substituting aluminum in the perovskite garnet crystal lattice, it causes a blue-green color. The vanadium concentration is usually low in perovskite, but there is one type of deep blue-green pyroxapacitin containing very high amount of vanadium that dominates the color of the stone. They exhibit a color shift, showing blue-green under daylight and blue under incandescent light. Many deep red, orange-red, or reddish-orange almandine color is attributed by a combination of iron 2+ and iron 2+, iron 3+ charge transfer. Iron 2+, iron 3+ charge transfer causes a strong orange color component in perovskite garnet. When the perovskite garnet contains right amount of vanadium and manganese, it shows color change phenomena. Two transmission windows, A and B, in the visible region are created. Window A is emphasized under daylight, showing a green-blue color. Window B is emphasized under incandescent light, showing a reddish color. The next common gem garnet group is eugrandite. Eugrandite garnets have 3 end-member species. They are andradite, grossular, and uvarovite. Different from perovskite, the X-dodecahedral site of eugrandite is dominantly occupied by calcium. The octahedral site Y is usually mainly occupied by iron, aluminum, or chromium, corresponding to andradite, grossular, and uvarovite. Iron 3+ causes greenish yellow color in andradite. The combination of iron 3+ and chromium 3+ attributes to the deep yellowish green to deep green color seen in some very rare andradite garnets. They are called demantoid in the trade. The orange-brown to brown in grossular is caused by both iron 2+ and iron 3+ ions. It is called hessonite in the trade. There is a very rare type of raspberry grossular. Manganese 3+ is responsible for the pink color. Vanadium 3+ or chromium 3+ or both are responsible for the deep green color in grossular. The vanadium 3+ tends to cause a more bluish green to pure green color in grossular, called severite in the trade. The chromium 3+ tends to cause a more yellowish green to green color in grossular. Chromium 3+ also can cause a deep green color in uvarovite. The next mineral I'm going to talk about is tourmaline. Tourmaline supergroup minerals are cyclosilicates, primarily composed of boron, sodium, calcium, iron, magnesium, aluminum, silicon, and oxygen with a complex structure. In general, tourmaline structure features 5 different cation sites of variable coordination. T site is a tetrahedral site. 6 silicon-oxygen tetrahedra form a corner-connected ring. At the center above the rings, there are 9 large 9-coordinated X sites occupied by sodium, calcium, potassium, and vacancy. Above X sites, in another layer, there are triplets of octahedral Y sites, H-connected octahedral Z sites, and boron-oxygen triangles. B and W sites are occupied by hydroxide, oxygen, and fluorine anions. To date, 36 species in tourmaline group have been recognized by International Mineralogical Association. Similar to corundum, tourmaline also shows wide range of color. Iron 2+ causes a blue color in tourmaline called indiголite in the trade. Iron 2+, titanium 4+ intervalence charge transfer causes brown to orange in dry white or U-white tourmaline. The combination of iron 2+ and iron titanium pair causes green color in tourmaline called verdilite in the trade. Vanadium 3+ and chromium 3+ can cause a bright yellowish green to deep green color in U-white tourmaline. This type of tourmaline is called chrome tourmaline in the trade. Manganese 2 plus is responsible for the saturated yellow color in tourmaline. Manganese 3 plus causes red to pink color in tourmaline. The red tourmaline is called rubellite in the trade. There is a very rare non-blue tourmaline called Paraiba tourmaline in the trade. It is colored by copper 2 plus. The name of the tourmaline variety Paraiba is derived from the Brazilian locality Paraiba State, where this gemstone was first mined. The bright blue copper-bearing tourmaline also can be found in Nigeria and Mozambique. The combination of manganese 3 plus and copper 2 plus or iron 2 plus attributes to the purple to violet color in tourmaline. Besides the typical non-blue color of Paraiba tourmaline, there is another type of sapphire blue Paraiba tourmaline. The color is caused by a lot of copper 2 plus and a little bit manganese 3 plus ions in the crystal lattice. Let's look at the whole range of color from yellowish green, blue-green to greenish blue in Paraiba tourmaline. They are mainly caused by a combination of copper 2 plus and manganese 2 plus ions. There is also a very rare type of reverse color change Paraiba tourmaline, when the concentration ratio of copper 2 plus and manganese 3 plus is within certain range. The color change phenomenon can be observed. The stone usually exhibits a blue to violet color in daylight and a blue-green color in incandescent light. Let's look at the color change phenomenon. The next gemstone I'm going to talk about is alexandrite. The most desirable alexandrites exhibit a lush green to greenish blue color in daylight and a warm, bright reddish shade in incandescent light. In crystal beryl, aluminum and beryllium occupy octahedral and tetrahedral sites in the crystal structure respectively. Chromium 3 plus substitutes for aluminum 3 plus in the octahedral sites to cause the color change phenomenon in alexandrite. If you are interested in learning more about natural fancy colored diamonds, you can watch a lecture named The Science Behind Fancy Colored Diamonds, presented by my colleague, Senior Manager of Diamond Identification and Research, Dr. Sally Magaya, in official GIA channel on YouTube. Besides helping us understand the chromophores in gemstones, the chemical information of gemstones also can help us detect the treatments. There is a type of ruby in the jewelry market. The fracture and cavities of this type of ruby are filled with lead glass, which significantly reduces their visibility. A large cavity can be seen on the table facet of a ruby under reflected illumination. Under a GIA binocular microscope with dark field illumination and fiber optic illumination, sometimes we can see blue flash effect or trapped gas bubbles that are typical for this treatment. This type of ruby may be unstable to chemical agents. Special care should be taken when cleaning or repairing them. Jewelers pickling solution etches the filler in minutes. If the lead glass in the ruby's fracture is removed completely, what is going to happen to the stone? Some large fragments can drop out from the original ruby. The ruby can even become powder. Besides using microscope, we can also use one instrument to detect the presence of lead in this type of ruby to further confirm and unravel this treatment chemically. The instrument is called Energy-Dispersive X-ray Fluorescence. The image shows the instrument used in GIA Carlsbad laboratories. The instrument is mainly composed of an X-ray generator, sample chamber, detector, and a data processing system. X-ray is a kind of electromagnetic wave with short wavelengths and high energy. Its wavelengths and energy range are between ultraviolet rays and gamma rays. When the continuous spectrum X-ray generated by the X-ray generator is focused into the gem sample being studied, An electron with ground state in inner orbit of an electron of an element atom is excited and being ejected from the inner orbit to form an electron hole where the electron was. An electron from an outer higher energy orbit then fill the hole and emit characteristic X-rays with a certain energy. We call this characteristic or secondary X-ray emitted by this element the characteristic X-ray fluorescence of this element. The wavelength or energy of X-ray fluorescence is related to the type of elements. As long as the wavelength or energy of X-ray fluorescence is measured, the type of elements can be known, which forms the base of quantitative analysis of X-ray fluorescence. In addition, the intensity of energy of X-ray fluorescence has a certain relationship with the concentration of the corresponding elements. The stronger the relative fluorescence intensity of an element, the higher concentration of this element. Therefore, quantitative analysis of elements can be carried out. When using EDXRF to do a qualitative measurement of rubies, lead glass-filled rubies show characteristic X-ray fluorescence of element lead, while rubies not filled with lead glass don't show characteristic X-ray fluorescence of lead. For most of the elements in the periodic table, EDXRF can measure them semi-quantitatively or quantitatively. However, EDXRF cannot measure elements that have atomic number smaller than sodium. For example, EDXRF cannot measure beryllium in corundum. At the beginning of 2002, some corundum treated by a new technology flowed to the world jewelry market without making any statement. The GIA research team, led by Dr. John Emmett Su, found that this is a new treatment named beryllium diffusion. By heating corundum at 1800 degrees Celsius with beryllium, colorless and light corundum can be turned into yellow to orange sapphires. This treatment can also reduce the blue hue in many black or dark blue sapphires to brighten their color. It can also reduce the purple hue in purplish red sapphire and increase its orange hue to produce very expensive paparazzi sapphires. Corundum of any color may become the object of beryllium diffusion treatment to change the original color. When the gem sample is immersed in the heavy liquid of methylene iodide with the help of a blue filter, sometimes a yellow diffusion layer on the surface of the gemstone can be observed. The color of diffusion can reach any depth inside the gem from the surface layer and sometimes even penetrate the whole stone. In order to not to miss the detection of any beryllium diffusion treated gems, GIA use laser ablation inductively coupled plasma mass spectrometer, simplifying as LA-ICP-MS, to measure beryllium concentration in corundum accurately. This is laser ablation inductively coupled plasma mass spectrometer at GIA's Carlsbad lab. It is mainly composed of a laser ablation unit for sampling and a plasma mass spectrometer. It is an instrument with high sensitivity and have an ability for multi-element repeat analysis. In the laser ablation system, the gem is ablated very slightly by laser beam. The very small fine grain of ablated gem powder was then transported while argon and helium carrier gas to the plasma torch. The temperature of the plasma in torch is very high, about 10,000 K. The high temperature atomizes and further ionizes the sample particles. The gaseous ions are then collected by the nickel sampling and skimmer cones, focused by the voltage lens, and enter the quadruple mass analyzer. Different ions are separated by the mass analyzer according to their mass to charge ratio, and finally reach the detector. The ion detector and signal amplifier convert the ion signal into amplified electrical signal used to further calculate the concentration of elements in gemstones. For example, in this illustration, 1000 ppm W iron is detected in this ruby by LA-ICP-MS. LA-ICP-MS has a lot of advantages of analyzing elements in gemstones. It has great speed, precision, and sensitivity. It can measure almost all elements in the periodic table, including beryllium, the key element for detecting beryllium diffusion treatment. The detection limits of many elements measured by LA-ICP-MS are very low at ppm level. The linear range of iron intensity signal is very large, from 100 up to 1 billion counts per second. A method can be built to measure trace elements at ppm levels while measuring major elements at percentage level in the same analytical run with very high precision. Most importantly, the method is minimally destructive and not impactful to the appearance of the stone. This picture shows 3 round laser craters on the girdle of a blue sapphire. The size of the craters are smaller than the diameter of most human hairs, effectively invisible to unaided eyes, and difficult to see with the 10x magnification triplet loop. The amount of ablated gemstone powder from 3 craters weighs approximately 3 millionths of a carat. LA-ICP-MS can help us separate most of the synthetic emeralds from natural emeralds. In this sodium-magnesium two-dimensional plot, natural emeralds tend to have much higher sodium and magnesium concentrations than synthetic emeralds. The chemical information obtained from LA-ICP-MS also can be used for species classification of mineral groups, such as tourmaline. The ternary plots demonstrate how the species of Paribas tourmaline set in this range is determined. The calcium-sodium vacancy ternary plot establishes the dominance of the X site in tourmaline, which is the first step of species classification. In this case, the stone belongs to calcic group. The aluminum, chromium, vanadium ternary plot determines the dominance of the Z site. In this case, the stone's Z site is dominantly occupied by aluminum. The lithium, iron, magnesium ternary plot indicates the dominance of the Y site, and finally assigns the tourmaline stone to one of the tourmaline species. In this case, the stone is the lithical-type tourmaline. Such as this rainbow-colored tourmaline bracelet. It was examined by identification and the species classification at GIA's Carlsbad lab. The tourmaline species ranged from red, pink albite and orange drywites to green-blue albites and violet-purple lithicotites. And there were 2 orange citrines that had been set between the 2 orange drywites in this bracelet. LA-ICP-MS has been used as the most reliable instrument for geographic origin determination of many colored stones in GIA laboratories. GIA colored stone identification and origin reports are available for ruby, sapphire, emerald, red spinel, Paribas tourmaline, and alexandrite. I use alexandrite as an example here to show the plots generated by using the trace element data obtained from LA-ICP-MS. In this 10 galleon alexandrite plot, stones from Sri Lanka, India, Tanzania, Brazil, and Russia are well grouped together and can be separated easily. Only stones from Russia, Zimbabwe, and Zambia showed significant overlapping. We can use other trace elements to separate them. In chromium vanadium plot, we can separate Russian alexandrites from Zimbabwean and Zambian alexandrites. Finally, we can separate Zambian from Zimbabwean alexandrites in vanadium boron plot. You can read the Gems and Gemology Winter 2019 issue to learn more detailed information and knowledge of country of origin determination from GIA's official website. This is end of the lecture. Thank you for your attention.
That is amazing. Can I tell you, most of it was over my head, Nick, because I'm certainly not a chemist, but you've opened so many avenues of curiosity for me. I just love that you touched upon the different areas of the world that the gems come from and how they differentiate in color, but there's some overlapping. That's fantastic. Can we field the chat group? Does anyone have any questions for our presenter? Yep, sorry, go ahead.
Yeah, I have a question. Can you hear me?
Yes.
Yeah, hi. In the beginning, you showed an old photograph of a scientist using a refractometer to measure the, I guess, the refractive indices of gemstones. I guess that's sort of an old-fashioned method, but can you use a refractometer to identify a gemstone, like whether it's a real diamond or a fake diamond?
No, you cannot. You have to.
Oh, okay.
No, you cannot. You have to use other large-scale instruments. More
okay. Okay. But why were they using a refractometer back then?
Sometimes if it's an imitation, for example, if it's a glass imitation, you can use a refractometer. But if it's a synthetic diamonds, you cannot use it to.
Oh, okay, okay. But if it's glass, you can tell the difference. But
yes, you can.
Oh,
yeah.
right. Okay, okay, right. Okay.
That is right. Rebecca says she found tourmaline in a creek in Maryland. That is pretty cool. So would a tourmaline found in Maryland, can you, off the top of your head, know the range of colors that you would probably find that in? Is that is that part of your background? Like, do you have a whole color library in your mind?
No, I don't.
That's pretty cool.
Because yeah, tourmaline has the widest range of color among all gemstones. It is possible it can come out from many types of colors or bicolor.
Rebecca says it was black. Black tourmaline is common in her town. Well, that's pretty cool.
In that case, it's iron-rich tourmaline. It's called shoral.
Yes. Yeah, the tourmalines in Maryland primarily are shoral, the black tourmaline.
Okay. That is very cool. And does anyone else have anything to share about finding minerals and gemstones in their area? You could stump the expert.
I found tourmaline up in Maine, I think. And that was many years ago. It was green.
Oh, beautiful, beautiful.
I was in Maine a few weeks ago and found tourmaline, so they're still finding it.
That's very
Greens,
cool.
blues, pinks.
Yes, that's beautiful. Yes, and they're surface mine, right?
Shallow open pits mostly.
Open pits, right?
So Nick, what is your favorite gemstone?
Oh, my favorite gemstone is alexandrite. I just like the color change phenomenon of this gemstone. It looks green under daylight, looks pinkish, looks reddish under incandescent light. I like that.
I have not seen that in real life. I think that would blow me away if I saw that. That's pretty cool. And so does your campus have students from all over the world?
Yes, yes. We have a lot of students from all over the world. I think from Europe, from China, from Korea, from Japan.
And then can you give us an example of what kind of careers they go on to have?
I think they can become a gemologist, working in a gemological lab, they also can become a gemologist as a salesperson to working in a jewelry store to
Oh,
sell jewelry. Yes, and they also can become appraiser to just evaluate the value of jewelry, and then they also can work in auction house to just to work in all the aspects related to jewelry.
wow. That's a whole lot of studying.
Yeah.
That's a whole lot of,
So if you take the gemological courses in GIA, you are going to have a very, very good, bright career, bright future.
oh, very cool. Well, I think we were super duper lucky to have you present to us. And honestly, the pictures of these gemstones are complete eye candy. I think you have a pretty darn cool career. You get to see these day in and day out. It's just
Yes, I
mind
feel very
blowing.
happy to see all those precious gemstones every
Oh.
day.
It is. It is. So what part of the world do you think the most exotic, or no, that's kind of open-ended. What part of the world produces the most precious gemstone?
Oh, actually, different types of precious gemstones are produced in different localities in the world. For example, the most famous place that produces ruby is Myanmar,
Mm,
and the most famous place that produces blue sapphires are Sri Lanka and Myanmar and Thailand. And for emerald, there are also other good famous localities. The most famous is Colombia, and also emeralds come from Zambia, come from Brazil, come from Afghanistan, come from Russia, come from many other places in the world.
that is a
So it
fascinating.
depends on the types of gemstones.
Very cool. Robin says thank you. It was a really well organized presentation and she learned a lot. I think we all did, Nick. I really do.
Thank you.
It was wonderful.
Thank you.
Yeah, I appreciate you sharing with us. Does anyone else have any final questions?
This is a really
Oh, there is one. Are
Yeah.
gemstones used for any functional purposes?
Functional, what type of functional? I think synthetic corundum have been used for in many scientific fields. For example, it can used to make lasers. And I think synthetic diamonds can be used in a lot of industries.
Right.
Yeah.
That is very cool. Well, we very much thank you for taking the time. You did spectacularly. This is great. And yes, Heidi, this will be recorded. We remember to do that. So